And here we go for lecture number 8 of the summer Haskell class. That date is wrong because I moved it a day, so obviously it's the 13th. You haven't gone back in time. Haskell is powerful, but it's not that powerful. At least not yet. We're working on it. So just for a review of type classes, we've seen the simple ones, equality types, that's EQ, ORD is comparison types, show is stringable types, things that you can convert to a string, read is of string types, things that you can read in from a string. Those are pretty simple. And then we have monoid, which is why can I never get that damn, there we go. Monoid, which it has an empty element or a 0, and it has an append or a plus element. So if this is from abstract algebra, it's kind of like a group, except you don't necessarily have inverses. So examples being lists are a monoid in any type. A sum type on the sum type on a numeric type, such as sum integer, is a monoid with 0 and plus. Product is a monoid with 1 and times. And then we had any and all, which are Boolean monoids. And we also have endo of A, which is a monoid on top of or isomorphic to A arrow A functions. And the empty is the identity function, and the append is the composition. Keeping in mind that monoids don't always commute. Some of these monoids do commute, but they don't have to. And then we talked about higher kinded type classes on our containers and our computational contexts of applicativeness and monadness, I guess one might say. Functor, the canonical example is a list. It's just a container of things. We don't really think of it as a computational context. It's just a passive collection. But then when we get into applicative and monad, we see that while lists can be treated as, say, a monad, or represents a multiple value computation, there are a lot of other things in them, and the concept is more general. So applicative and monad are two notions of effect. Applicative is where you know the structure up front, and the monad is a computational context where your intermediate values can change the structure on the fly. So now we're going to cover 2 more type classes. One is called Foldable. These are sort of the 6 canonical. Someone say something? Oh.
Just quit my job. Sorry.
These are the 6 canonical fold functions, and the minimum representation or the minimum implementation is either fold map or fold R. You implement fold map or you implement fold R, and it will derive all the others for you. And for those who don't believe me, I'll go over a couple examples in that vein. But fold map is the fundamental method. Remember that fold map is the one that takes a function that maps your A's into a monoid, and it takes the foldable collection and it returns a value in that monoid. So it maps everything together, or it maps all the A's into a monoid M, and then because M's are innately reducible with M append, you get a consolidated M, an aggregate. So on a tree, this is a infix tree. So you've got a left branch, a right branch at each node, and then you've got a value. We say that fold map on the empty tree doesn't matter what the function is, it's just mempty. And fold map of f on a node is it's the result of fold mapping on the L, and I need to put an F there, so let me fix this right now. Because obviously that wouldn't type check or make any sense. So now I fixed it. Fold map f on the left tree, m appended to f of x, m appended to fold map of f on the right tree. And you can implement all of these from fold map alone or from fold R alone. So just to review these briefly, fold is fold map of id. Fold is the function that can be used if your traversable is already in a monoidal type. And then fold R can be derived from fold map using endo. And you can also derive fold L either from endo or fold R, but it's pretty complicated. And to do it efficiently wouldn't fit on this slide. So you can look it up in the implementation, or you can just trust me that it can be done. And then here we have, do we have anything new? Oh, we just sort of recall the endo monoid, which is a monoid on functions. Fold L1 and fold R1, the way that you get those is you write analogs of head, tail, last, and that all those list functions, quite a number of them can be turned into foldable functions, not necessarily efficient. But for example, if you wanted a foldable last, you could do a fold left of the function that takes x and y, throws out the x, and returns a y. And we give it an initial value of undefined, which means that it's going to fail if you throw the empty foldable at it. Well, we know that that's exactly what last on the empty list does. So yeah, I mean, there are a ton of these in the source code for data.foldable. Right. Fold map can be implemented in terms of fold R using mappend and using mempty. Let me just correct an error that I made down there. Oops. There we go. The canonical foldable is, of course, the list. And our fold map, you give it any function and the empty list, and it's going to say, well, I don't have any m's, where m is the monoid value that you're mapping into. I have no m's, so I'm going to return m empty. And if you have a cons, that is a non-empty list, x cons x's, and a function f, well then you apply f to x, that gives you an m, and you append it to the result of fold mapping f on the x's. So it's, classic recursive definition, and for foldable and traversable, which is what we're going to discuss next, that's almost invariably what you do. These are very straightforward implementations, and that's good. That's what we expect. We want these to be straightforward and easy to understand. A map, remember map is a two-parameter type. Map KV is the map from key type K to value type V. And we are creating an instance for map K, for any K, of foldable. So what we're doing is we're folding over the values and we're just ignoring the keys in this particular case. So we use a function called minView, which takes a map and it either returns a just of the minimum element and the rest of the map, or it returns a nothing if you throw the empty map at it. So it's a total function. So when minView m is nothing, well, then we say there are no values in this map, it's the empty map, and the fold map is mempty. Otherwise, we get a value called low. We throw that into f to get an m, and we append it to the fold map of f on the rest of the map. And finally, foldable maybe, and there are a few others like this. Fold mapping anything on nothing is mempty, and if you fold map f on just a, you're going to apply f to a. So you're treating maybe as a 0 or 1 element collection, which kind of makes sense. Before we go further, any questions?
So foldable takes a one argument type constructor.
Yes. Foldable, like functor and monad and applicative, is a higher kinded, it's a higher kinded type class. Yes?
This might be a little bit below where I should be at this point, but when you say fold map F, you say, you know, fold map, you're defining fold map F for the pattern that matches just A, like, you know, and then you're saying that equals applying F to A, right? F, you know, applied to A. When I, like, does that mean that returning the foldable, like the return value of that function is specifically whatever F with A as an argument returns? Or are you actually, like, you don't return it wrapped in the monad, do you?
No, it's not wrapped in the monad, and in this case, it's not wrapped in a foldable either.
Okay, so that makes more sense. I thought, like, I was thinking that that's why you would fold.
So yeah, I mean, the general, so I mean, that's interesting because, let me actually bring up, this is pretty abstract stuff at this point. I mean, you know, usually when you want a foldable, you want a list, but foldable is more general. So when you're fold mapping, I don't know, see if that, you know, when you're fold mapping something like that, it's an aggregation. Of course, you can also build back up the collection. Something like that, where, you know, your fold map is actually building the collection back up. And I'll get into cases where that's the behavior. Because map, the list map, or, you know, the more general mapping of a function across a collection, that can be written as a fold. So here are some derived functions for foldable. To list, turn it into a list. Null, length, lm, maximum, minimum, sum, and product. We thought of these all as list functions. They're actually more general. They're foldable functions. So what is a foldable? It's a collection where aggregations over all of the elements is an accessible concept. It makes sense. And I'll get into what that means exactly. So the arrow type on R, arrow R, or R domain functions, that's a functor because you can think of it as a container. You can think of it as an R-indexed container. But you can't fold over it because you can't fold over all the possible R's. Another foldable is data.sequence.seek, which is it's like Clojure's vector type, which is a little bit misleading insofar that as it's not a linear algebra vector. It's a linear collection designed to be finite, but it's much faster on many operations than a list. So we have an append operator, which is the angle brackets that are meeting each other. We have a cons, we have a snock. Snock is when you append. We have a take, and many more on seek. And it's got the same fold map semantics. The difference between seek and list is implementation. Seek is a finger tree, so it's got very fast indexing, concatenation, subsequencing, and what you lose is the ability to create infinite ones, which you can do with lists. So for example, we let s equal 5 seek cons itself, and just looking at the type, it looks like that's okay, but as soon as we try to take 5 from it, we don't get 5 elements, we get the world blown up. And that's the third line where we're doing seek.take 5s. And then we do let s equal 5 cons s, the cons being the seek cons, in s. And then that lowercase seek is the evaluation forcing seek. So it's an unfortunate accident that has the same name as this collection type. And just the evaluation of that thing, just forcing it to weak head normal form is enough to blow up the world. So seek is designed to be finite, but it's a foldable. We also have data.text is a string type that is much more efficient than lists of characters. That I don't know if that's fold. No, I take that back. It probably has some foldable-ish interface, but it's not a general collection. So I spoke too soon. So arrow R, but it's not definite. What I mean by definite is computably enumerable. So it's almost the same notion as mathematical countability, but it's a little bit stronger. Definite meaning that for a list, even if it's infinite, you can compute all the positions, and you can traverse it. There's a computable way to traverse it. But with general R index containers, like if R is int arrow int, well, that's not even countable. So you wouldn't want to fold over that domain. On the other hand, so let me actually step back. So functor means that it's structured, but it doesn't necessarily have to be definite. It doesn't have a notion of all the elements necessarily. Set, on the other hand, is definite. In fact, in data.set, it's finite because there's a tree structure, but it's unstructured because it depends on equality semantics. So it's definitely a foldable. You could say, what are all the elements of the set? But because it's structureless, it's not a functor. And now we get to traversable, which is where it gets really interesting. Traversable has to be a functor, and it has to be a foldable. Before I talk about traversable, let me back up and say that even though you can have an infinite foldable, the only time that doesn't behave pathologically is when you're folding into a monoid that has some kind of termination. So the example that I showed earlier, where my monoid was Boolean, was all, or was any, and it's an infinite list, but you only need one success to stop, then fold map will work. But in general, folding across an infinite collection means an infinite amount of work. So it's usually pathological, not always.
Again, how it knew to stop. Like it's the
any is just it's a function to tell you when if any of the things in the thing that you're folding across match a predicate.
Yeah, but how do you do that without like hard coding the behavior of any? Like how does it work on a general foldable level? Does that kind of make sense?
Yeah, sure. So the example that I'm talking about is where you have this guy. And any is a monoid wrapping a bool, and it's defined as the empty is false. And then
because the assumption is that once you get the empty, then a foldable always terminates, or
well, okay, so once we get to
like how does it know that it can't flip from false to true? Sorry, from
because the monoid, the M-append, which is this diamond, is defined in terms of OR, which is short circuiting. So if you have true,
okay, I see.
then that's true.
I see now.
It's going to short circuit to true.
Got it.
But it's only in short circuiting cases where it can say, okay, I'm done with this fold. I have the final answer. It's only in that case that a fold map on an infinite collection can terminate. So in general, it doesn't. So, and that's actually relevant to traversable too, because traversables are collections that are usually designed to be finite, but I mean, list is traversable and can be infinite. So, you can have an infinite list, but usually when you think of traversing something, you think of it being finite. Because, well, now let's get into what traversable is. Traversable has this funny looking type signature. A traverse takes a function a arrow fb. And if you recall, and f is an applicative. So if you recall in the Cleasley arrow interpretation, that is an f-effectful function mapping a's to b's. And then traverse returns from that function, that traversal function, it returns a function that takes a traversable of a's, or t of a's, and it returns f of t of b, or f of t b, which is saying that it turns a t of a's into a t of b's in an f effect. We also have sequence a, which is the analog of monoid, or of monad's sequence. That's traverse id, and that takes a t of fa and turns it into an f of ta. So that's a way of commuting your two type constructors.
Wait, I don't understand how traverse id makes sense when the types don't match up. Right? It is always going to be a to a, but there you have a to fb.
You're absolutely right. Let me.
I mean, unless f is like, I guess, trivial, but no, that doesn't make sense. Is there a functor that just gives
Let me think about that.
the type itself back, like the trivial functor or something?
Now I'm curious. I wanna.
I mean, it's probably like some sort of auto-inferring thing like that, but
T traverse. So the type does match up, and I think.
oh, your A is FB. Okay, got
Yeah,
it.
your A is
Got it.
FB.
And it infers that. Okay, because it's the only thing
Exactly.
that makes sense. Okay,
Yeah,
makes sense.
that's what I thought. I mean, that's kind of like how with monads we talk about. We have our join operator.
Because the right side imposes structure and the left side doesn't, so you can turn your A into that FB.
Yep.
But you couldn't turn your right side into an A.
Yeah.
How it does that computably is beyond me, though. Like, it seems to me like you could blow up the type checker by just constructing like an elaborate sequence of.
Oh, I can show you how to blow up the type checker. It's actually very easy if you just do.
Oh, see.
It's solving a
Just do it
system.
after those, okay.
Yeah, it's solving a system of equations, and it's exponential in the number of ids. So if you do like 50 ids, it will take forever. But what I was getting at is the join operator on monads, which takes you down. It's sort of your limited inception kick. It can't take you out of the dream monad, but it can take you out of a dream within a dream. Join is just defined as return id. And because it's, yeah, we can talk about that offline. Obviously, I think this stuff's super cool, but I do have territory to cover and dinner to eat, which hopefully won't be freezing cold by the time I get home. So yeah, we have traverse and sequence A. We also have map M and sequence. Those are familiar monad functions. Traverse and sequence A are just the applicative analogs. So those will work with all applicatives, and that's actually quite important to us, as we'll see later. So yeah. So let's talk about the motivation for traversables. Like, why do we care about this thing, and what does it have to do with traversing? Because when I first saw that type signature, I was like, what the hell is that? I kind of had to jump into the deep end with Haskell because, I was teaching myself, and therefore I didn't know that I was jumping into the deep end. It was, not a well-marked pool. In any case, so we're doing a traverse. This traverse underscore is something I wrote. It's just a traverse that throws away the value. But this effect, so it's purely effects. So we do this traversal of put stir show x plus a comma on this list, and it prints them out. We're traversing with an action, an effectful function. And then the second example is one in the writer monad, where our traversal is, okay, first tell, that is, put something into the log of the writer monad, that you're squaring it, and then return the square. And we apply that to this tree, which has a 1, a 2, and a 3 in it, and we get back as the return value the tree with 1, 4, and 9. And in our log, we get squaring 1, squaring 2, squaring 3. And just remember that since traverse works with applicatives, it will also work with monads, because all monads are applicatives, not vice versa. So if you look at traverse and you think, oh, that's only useful for applicatives, well, I have good news, which is that monads are applicatives. If you're using 710+, if you're using 7.8, then you have some work to make that happen. So traversable, what is it? It's structured like a functor. It's definite like a foldable, but it gives you this interpretation that pertains to the effects. You're saying, I want to map an f-effectful computation from A to B across this traversable. If you know how to do it, then you have a traversable. Did that make sense?
Mm-hmm.
And just to underscore this, we have the type signature of fmap, which takes a pure function, no effects, just mapping over the container, and a traverse, which takes an effectful function and maps over the container. And so now we can finally answer, where is the for loop in Haskell? For is just flip traverse, and that's your for loop. So list is the canonical traversable. Traversing anything on the empty list, no effect, so it's pure, and you return the empty list. Traversing G across X cons X's, we're building up a cons, and since the cons function is a pure value, we don't need to do any effect to know that we're doing a cons. We fmap that across G of X, which is potentially effectful, app traverse G axis. So again, that's a recursive definition. With trees, traverse blah empty is pure empty, doesn't change the structure of the tree. Traverse f node LXR is node fmap traverse FL, so you do the left traversal, you app that to FX, and then you app that to the right traversal, and then you collect it all up into a node.
I think I did this once in like 1,000 lines of R.
Okay. So yeah, you can do it in fewer lines of Haskell. You can get functors fmap, and you can also get Foldable's foldmap from traverse, and because I'm pedantic and thorough, we are going to. So recall the new type, or recall the identity. Identity is a wrapper that says, it's just does nothing. It's the no-op. So as an applicative, it says, I'm a computational context that does nothing. And as a monad, it says, I'm a computational context that does nothing. So we fmap, to fmap f across the traversable, we traverse. Now traverse has to take an effectful thing. It can't take an A arrow B, it has to take an A arrow, I'm gonna call it G, where G is some applicative, has to take an A arrow G B for some G. So you just say, okay, well I don't want a G, but it's making me give one. I'll use identity as my G. So that's my applicative G. So identity.f is going to take A's into identity A's. You traverse with that, and then you use run identity to get out of the identity monad. And that's how you fmap across the traversable. So what about fold map? Well, this is going to get really cool. There's an applicative called const. Does anyone notice anything weird about this?
Don't use B.
Exactly. We don't use B. It's called a phantom type. It has nothing to do with the value. It exists at the type level, but in the value level, no. And what it's kind of sort of conceptually saying is that it's an A. It's really an A, but we have some type level relationship to B, even though it doesn't contain any B's in it. And that's actually going to make sense, even though it seems like it shouldn't. So if A is an equality type, then const A B is an equality type. Even if B is not, it doesn't matter because it doesn't care about B's. Functor, const is always a functor, but the fmap doesn't do anything because the fmap would be mapping, we're const in A, so the fmap would be mapping some B into C, where B and C have nothing to do with A, so we don't even look at the function. You know, fmap of anything on a const is a no-op. Foldable, well, const A as a container of B's, it's always empty. So you don't even have to look at the arguments, you just return M empty. Const is also traversable, not a very interesting one, but you have no effect, you return it purely. So you're probably bored with some of these, like this cat is, that's why he's yawning. This is the money shot. This is the one that matters. So I did not intend that to be a porny reference.
You should have said the monoid shot.
The monoid shot, yes.
There we go.
The monad shot.
Yeah.
This is good news for women in Haskell.
Yes, yes. Well, problem with monad talk is, you know, bindage and discipline.
Everything was out of post, right?
Anyway,
I'm sorry for listeners of your video.
He's gonna edit that one out.
no, I'm not. Fuck it. Monoid M implies applicative const M. Remember, a monoid is a type that has an empty and it has an append, so it can collect things. And the instance is pure on any value is just const M empty. So we're just saying, well, we had no effect, so we're putting M empty in that monoid. And if you app two consts together, remember the E1 and E2 are in the monoid, and the value, the second value of the const are something, but we don't care about it really because we don't have them kicking around. That's const E1 M append E2. And so as a computational context here, const MB is a world where we just ignore the B. You know, we don't even really compute it. But we do go through all the effects that would be involved in getting that B. And we append them together. And those are type M. Why is this important? Because const M for some monoid is an applicative. So if we want to fold map G across a traversable, we can use const.g. So in the middle, we see the fold map type signature and we see the traverse signature. And it seems like they're irreconcilable. It seems like, well, traverse requires an A arrow FB, and fold map requires an A arrow M, where M is some completely different monoidal type. But const MB is a way of saying M in terms of B, the constant M in terms of B. So we're ignoring B. And that's applicative. That will actually, this seems very dry, but it's actually extremely useful because with constant identity, we can take forms like traverse that require some kind of wrapper, and we can make it apply to when we don't have a wrapper too. So that's how we say traverse is the general form, fold map and fmap are subcases of it. And when we get into lenses in 2 classes, because they decided to put a class on system programming in before we get to lenses, you'll see that more concretely. Traversable laws. Traverse identity is identity. That means that the traversal that doesn't do anything, doesn't do anything. Or the traversing with the function that doesn't do anything, doesn't do anything. That kind of makes sense. And we have a composition law that allows us to fuse two traversals into one with an F map on the G to get it to go one level down. But that allows us to fuse two traversals into one. And what these tell us, what the consequences are, well, if you traverse with pure, you get pure. So the pure traversal doesn't do anything. It just lifts it into the applicative. We have that traversals visit every element exactly once, which kind of makes sense because otherwise it wouldn't be a traversal. And finally, they either preserve the structure entirely, such as with fmap, where your mapping is rebuilding the structure. You have a structure in A's, you're building the same structure in B's, or they tear it down completely as in a fold. But you don't get like a modified structure that has like some of it and not other stuff.
So what if you had like a graph and you wanted to apply a transformation to a subgraph, like only to certain nodes? How would you do that with traversable? Or you can't?
Yeah, I don't think, so as I think about that,
Would you need to lens into like the subgraph somehow and then do traversable on the subgraph object, but then somehow have it like, because it would have to reconstruct the full graph, right?
well, the way I think of graphs is as sets,
Mhm.
like a set of nodes and then a set of edges. If you think of it in terms of sets, then it's not a functor. And of course, graph also has, I mean, the other thing is that generally when I think of a graph, I think of it as having a node type and an edge type. And then some way, you know, there's a node type and there's an edge type, and the edge type has some kind of functional dependency on the node because, I'm sorry, the edge
Wait.
type implies the
What
node.
am I saying? Yeah, the subgraph, well, the subgraph is determined by like the nodes. Like for example, if you want to do something, like let's say all the nodes are integers and you want to do something called even integers, you can just include that in the function that you're giving to your traverse operation. Right?
Yeah, sure, but I mean,
But I guess that's not-
computationally,
Like I usually don't want to do that.
but computationally, you're always, computationally, you're doing the same thing to across the whole structure. Now that
Yeah,
function
that's
that you pass in, I guess it could be, that's interesting because I mean, you can implement filter as a fold, right? So yeah, I have to think about that. In any case, moving on before I get out of my depth, I actually had to research Traversable a little bit because, so this is actually not my idea. The part about traversals, how they either preserve the structure entirely or destroy it. I think what that means is more at the type level. You know, when you do a traversal, you know, your traversal will either preserve structures of that type or it will throw them out. In any case, you generally don't want to write traversable instances by hand. What you want to do instead is use a language extension called derive traversable, which adds traversable to the list of things that can be auto-derived. You also have to derive functor and foldable because those are mandatory superclasses. And
Can you remind me how derive automatically derives using more complex types like this?
I can try. So with a functor, there's a clear structure that's laid out, like item A would map to item B, and then list of list tree A would map to a, oh, I actually screwed this up in terms of notation, but it would map across the lists using the functor there. Now, obviously, there are some types that can't be made into functors, and so with those, it would fail to derive. And then with foldable, it would probably just treat it as a bare container So if there's an A, then you say I got one A out. And if there's a list trees of A's, then you append them. And then traversable, it's the same thing that I did earlier in the class. I mean, it's all very mechanical.
Okay.
I'm trying to think if there's ever, so obviously like left to right fields, it's going to traverse the left field before the right field. It's going to have that convention in it. Because traversables have this ordering of effects that is implied. Yeah, I mean, I'm sure the derivation process on arbitrary types is complex, and also the determining which types you can do this on and which ones you can't. Because you could probably make your tree-based set type a functor, it would just be mathematically wrong. So here we have an example. We're traversing with the print function on this list tree with the items 2, 3, 5, 7, and we get them printed out. Yeah, what's up?
Quick curio. The pipe operator, like you're talking about sort of deriving, like it wouldn't, sort of the pipe operator would be like not infix, would be sort of like.
What do you mean? That's just syntax.
Yeah, I understand.
The bar that separates the cases, right?
But like, if you think of it as an operator, then you can use like, actually, I don't know how to explain it. Like it's a type constructor. Like it's a higher kind of type in and of itself that like generates a union.
Well, no, this would be done using template Haskell.
Yeah.
Because item A is a type expression.
Yeah.
You're operating on the syntax at that point, and template Haskell can get very gnarly quickly. So
I was just wondering if like if you, I don't know, like you can use, I'll talk to you about that later. Like you can use that as like things like the higher kind of type to build a union.
Well, no, deriving to create new deriving instances or new derivable type classes, you probably have to use template Haskell, especially because there are instances that depend on how they're declared. So for example, if you declare something with record syntax and you derive show, it will print in record syntax. So some of those have to be done with template Haskell. So enough about traversable. Let's talk about language extensions. They're compiler specific, but almost every Haskell deployment uses GHC. The only one I know of that doesn't, I think Standard Charter uses Hugs because they have like 120 people or some large number like that, so they can use whatever they want. But we're going to be using GHC. And at the interactive mode, you can either set -x language extension and turn it on, or you can put a language pragma in the file and it'll apply only to that module. You could also pass it in as a command line argument, -x language extension again, but I've never seen that done. In fact, I don't know why you would ever want to apply a language extension to your whole code base. Derive functor, derive foldable, derive traversable, those allow auto derivation of those type classes. Now in GHC 710, all you need to do is use derive traversable, and it's going to bring in functor and foldable. But in 7.8 or less, you also need those, unless you are going to write those instances by hand. Bang patterns allows you to force evaluation. Now it only goes to weak head normal form, so it's not going to go deep into your nested data structures, but it will bring it one level of evaluation through. So for example, we have let f x bang y z equal x, y is unused, but because of the bang pattern, it still gets evaluated. So if we try to evaluate f5 undefined 7, it blows up. Why do you want this? Because in high performance code, you often want to know exactly when things are evaluated, and you want to be able to control that. View patterns allows you to make a pattern that instead of matching the top value in the case of expression, matches the result of a function applied to that, and that function is called a view. So here we have a view pattern, sum to 0, where we're saying, okay, if sum applied to the argument, and that argument is a list of ints, equals 0, then we return true, otherwise we return false. So it just makes your code a little cleaner, a little nicer. This isn't really adding new capabilities to the language, it's just making it prettier. Here's another more typical case where you have this config, which is a data type. You say case config of, and we say, okay, when dry run is true, you don't want to make this like a nested if else blocks. You want to say, okay, let's go through the cases. If dry run is true, that's the view pattern up top, I want to do dry run. That's some function I have. If limit matches the pattern just x, and then we have a guard of x is less than 0, I want to throw an error. And in any other case, I want to do a default run. So again, it makes the language prettier. Sometimes you want to use it, sometimes you don't. Overloaded strings. This is one I use a lot because when you're working with more heavy-duty string parsing, you're almost never using the default list, or the default string, which is a list of characters. So if you set overloaded strings, then the string literal will be, as we see in the middle, an A, where A is in some type class called isString. That could be a list of characters. It could also be a text. It could be a byte string. It just gives us more options. And it means that to create a text or a byte string, we don't have to create the string literal and then call a function to turn that string literal into the text or the byte string. We have safe, which blocks unsafe behaviors. Unsafe perform IO is a function that takes an IO of A and returns an A. You might ask, why would you use this? The answer is you almost never should, but there are cases. Usually it's when you're working with APIs and combining functions in a way that the type checker can't prove is side effectless, but you know that it is. But you should never, ever, ever use unsafe perform IO on something that does have side effects. Unsafe coerce allows you to map any type into any type. And that's subverting the whole type system entirely. Again, I've only found one occasion to use it in my whole life. And even there, I think it was probably not the right thing to do. It was the quick thing to do. I was converting a floating point to a 64-bit word. With safe, you prohibit all that unsafe stuff. If you use the language's extension safe, then everything you import has to be safe, and these things that are unsafe are disallowed, and you get a compiler error. So it forces you to use a subset of the language called safe Haskell. Generalized new type deriving. This is a function that allows you to derive type classes that exist on a wrapped type. So a new type is wrapping another type, we'll call it the old type. And generalized new type deriving allows you to take type classes on the old type and make them apply to the new type. So here we're wrapping a list, and we say, you know what, we want its monad instance, and we get it. And it can be powerful and neat, but it can also be dangerous. The reason it can be dangerous is because there's a pattern called smart constructor of saying, you know what, I don't want my type to be able to hold every value that the fields say it can hold. And generalized new type deriving can be used to break the smart constructor pattern. And that's a problem because if the original type only follows the type class laws, which you do want to follow because otherwise your code can not only is it bad practice, but the compiler is aware there's type classes that might make incorrect optimizations. Well, with generalized new type deriving, you can create a type that inherits type classes from what it wraps, but because it doesn't follow all the invariants, it can create false or non-compliant type class instances. And there are a couple other things that are more corner casey, and it is getting better, but historically generalized new type deriving has actually been very controversial. Empty data decals, that allows you to create an empty type, which has nothing in it. The old way that you would do this was you would say data void equals void, that's a constructor, of void, which is the type void. So that's a little confusing, but you're essentially defining a type in terms of itself, and what that, in terms of itself in a way that it can't reasonably recurse. Because I mean, you define list in terms of itself, but you have a base case. When you define void in terms of itself with no base case, you're essentially saying I can't create one, but that's confusing as hell. And with empty data decals, you can just say data void. It's an empty type. Why would you want to do that, though? Well, one reason is for documentation. You can say that your function never returns by having it return in an empty type. Another reason for it to exist is because types are actually mappable to statements in a logical system called intuitionistic logic. Your unit type, you always have a unit type, so that's true. Void is false. A single constructor that is a product type of an A and a B, well, having a C in that case means that you have an A and a B. So that's a conjunction. A union type, C2 of A or C3 of B, that means you have an A or a B. An A or a B function is analogous to A implies B in intuitionistic logic. If you want to say not A in intuitionistic logic, the way that you do that is you show a function that takes an A and returns void. So these types actually map to a field of logic, which is very interesting. Intuitionistic logic is logic where you don't have proof by contradiction, or you don't have the law of the excluded middle. So rather than reasoning about things being true or false, you're reasoning about things being provable or not provable. I can't do it justice in the amount of time we have, though, so I'll just punt on that part of it. Finally, phantom types, which we've seen with const. Another example is this vector type, which has a type level nat being a non-negative integer. Data vector NA, it's a vector of A's of size n. So we've got a constructor empty, which returns a vector 0A. We've got a cons, which takes an A and a vector NA and returns a vector n plus 1A. So when you want to, at the type level, make sure that you're not doing dot products of vectors of different lengths, you can do that with all this stuff. Now you're bringing in a bunch of a bunch of language extensions to do it, but it's there. And of course, the nat types are phantom types. So we have this vector 3 int, which has, it's a cons 101, cons 103, cons 107, empty. There's nothing of type 3 in it. The type 3 doesn't have inhabitants. It's purely a phantom type.
So that's for type checking the length of the vector?
Yeah, what you would use that for is linear algebra, for example, where you're dot producting or you're taking a dot product of two vectors. It's not well defined unless they're the same length. Also, matrix multiplication has similar constraints, m by n, n by p. You can actually take this even further into a concept called dependent types, which Haskell doesn't support right now, and which I'm not even going to talk about because I'm just not qualified to talk about it. Like I'd have to do tons of research before I could even give a half-hour lecture on it. But it is cool, dependent types. And this is sort of getting toward that. A dependent type, the idea is that you can take a value into your type system, which allows you to put arbitrary computation in your type system. So the good news is that your type system can do anything. You can put any invariants you want. The bad news is that because you can do arbitrary computation in your type system, your typing is no longer decidable. The halting problem. But that's way in left field. You don't need to know that stuff to build production Haskell code, that's for sure. Flexible instances. Back to earth. This is a common one. You'll see it a lot. We have a type class called describe. It's kind of like show, but gives a little more description. We have an instance describe int, and then we have an instance for strings, which are lists of chars. And this is actually illegal in vanilla Haskell. You can't write an instance declaration for a specific case of a parameterized type. So you could write a describe that applies to lists, but you couldn't write a describe that applies to lists of chars. It's almost like the nightmare you get with type erasure in Scala, where you can use the outer type, the container type, but you can't do things with the inner type, at runtime that is. However, you can use flexible instances and then they'll compile just fine. And flexible instances is pretty vanilla. People aren't gonna roll their eyes if you use it. Now we come to overlapping instances. With flexible instances, we're just relaxing that qualification that it has to be base type. We're saying, yes, you can write a type class instance for concretions of parameterized types. Overlapping instances goes a little further because now we're saying, here's an instance to describe a list of A's, where A is any show type, and we have a different instance for a list of chars, and they overlap. If you have a list of chars or a string, then both instances should apply. So overlapping instances is what you use to make that not a type error. And the way overlapping instances works is, in this case, it will use the most specific instance that there is, which is all fine and good, as long as your type class system is simple. But sometimes overlapping instances can get hard to predict. And in general, if it's not blindingly obvious which instance applies, you probably have a design flaw in your system. GADTs, this is one of my favorites. It allows you to represent your data type by giving, rather than giving constructors and the fields, you give the constructors by the types of the functions, of the constructor functions. So in this maybe case, it's really just a syntactic transformation. We're saying maybe A has a constructor called nothing, and it has a function called just that takes A's and turns them into maybe A's. But there are things you can do with GADTs that make them more powerful. So in this example, we have array of B, where bit array takes an integer and turns it into an array of bool. List array takes a list of A's and turns it into an array of A. And text array takes a text and turns it into an array of char. So what we have there is, rather than saying array of B equals blah, 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 we give the constructors, and by giving the constructors, we have more control over what that B type is. And that B is kind of a phantom type, because a bit array wrapping an integer, it doesn't really have bools on it. We're just using it as an interface to bools or to bits. You know, we're saying that, okay, if I have a bit array around 37, then what I really want is I want index 5 to be 1, I want index 2 to be 1, and index 0 to be 1. So then, yeah, with this GADT, we can write a function called @, which will go into either any of these array types, and it will do the right thing in a type-safe way. And I can't really do GADTs justice in 2 minutes, but that's just the start of it. So yeah, those are very useful. Multi-param type classes. That's multiple parameter type classes, exactly what you think you're getting. You can use that to express relationships between types. So here we have a 3-parameter type class, multiply ABC. We say scalar times a scalar is a scalar. That's our first instance. Scalar times a vector is a vector, so we have an instance for that. Matrix times a scalar is a matrix, an instance for that, and so on. Now, one of the problems with multiple parameter type classes is that if you have a fan out in terms of your possible types, you can get a combinatorial explosion. You know, as with relational joins, because your type classes become relations when you have multiple parameters. So an example that isn't really a combinatorial explosion, it's just ugly, is we have a class convert A, B, and that has a member called convert, which is A to B. We have a string to int and a string to integer, and then if we see convert 21 in code, what is it? If there's some kind of context clue, like we use that value later on, we might know, but in general, that could be an int, or it could be an integer, or if there's another convert instance, it could be something else. Functional dependencies allow you to say, okay, this relation is actually a function, or class multiply ABC bar AB arrow C. What you're saying is that C depends uniquely on A and B. You know, so when you're multiplying a scalar times a scalar, you know that the only type that it can produce is a scalar. You multiply a scalar times a vector, you know that it can only produce a vector. And that narrows down your search. It makes your compiler a lot happier. Aesthetically prohibits a lot of things that you don't want. They're used heavily in the monad transformer library, the MTL. So as I discussed before, even though I talk about the reader monad is actually a type class. So there's not one reader monad. There are reader monads, which is the type class monad RM. M is given a kind hint to just say that it's a type constructor. It's not a concrete type. And we're saying that M determines R. So it's a functional dependency. And that makes a lot of sense because, for example, here I'm using monad state. If M is state t int IO, then S is going to be what? Been talking 100 miles an hour for, for a while. Okay, so you guys followed the functional dependency stuff though, right? Okay, so it's essentially saying that this type class, which is a relationship between types, you're saying that this relation is actually a function, like M uniquely determines S. So when we say monad state SM, that means that M is a state monad of S, and S is uniquely determined by M. So a monad can't be a state monad of two different states. So with state t int IO, well, it's a state monad of int. The S is uniquely determined by M. And on the case on the bottom, we have a stack. We have a writer t list of strings, state t bool, identity. That's a monad transformer stack. But the state transformer that we're using is using a bool for its state. So from that M, from the monad that we're saying is a monad state with some state S, we know what that state is. Probably worthwhile to review these slides. I'm almost done. There's a lot of material today. Rank n types. So the type of the empty list is, we call it list of A. It's actually for all A list of A. It's the only thing that is a list of A for every A. Id, the function, is for all A arrow A. But rank n types allows you to put your for alls, your quantifications, inside your types. So, question. What's the difference between the type up top, which is quantity for all A dot A arrow A to int, and the type on the bottom, which is for all A arrow int? What's the difference?
on the left, it can be functions that take any arguments to int, whereas on the bottom one, it has to be, the A is fixed, if you will, for each instance, right?
No, not quite.
Okay. Like what I meant to say is like, is the top one is like,
Which one's more restrictive?
the bottom one,
Why?
because the top one can,
Okay, let me back up. Which one is more restrictive in terms of, these are both functions. You agree with that, right? Which one is more restrictive in its argument?
in its argument.
Yeah, which one takes more arguments? Which one is,
The bottom one.
the bottom one takes more things.
Oh, I see.
Yeah, that's correct. That's correct. So what's an example of something that you could pass to the second function that you couldn't pass to the first function? Okay, I'll give the answer. So the rank 2 type above says that says that you have to pass it a function that can handle all A. So
Yeah.
it's saying you have to pass me a function that,
That's what I was trying to say
Yeah,
at any end of it.
exactly. But the one on the bottom is saying, yeah, for any A that there is, I can turn an A arrow A into int. So the less F1 is the one on the bottom, the more permissive one. In both cases, we're just defining these to be constantly 3, so we're not doing anything with the function. F1, you pass it id, and it works. You pass it reverse, which is list of B to list of B, and it says, well, yeah, that fits the bill. Returns 3. F2 requires a function that is A arrow A for all A. So id, it will accept, but reverse, it's going to fail on. Just a little bit of explanation about type parameters and how the language thinks about it. So if you have last, that's the function that takes a list of A's to A's. I just pulled something. It's actually, that's a shorthand for all A, list of A arrow A. You can also think of that as a, getting a little meta here, as a function that takes a type A and returns, and that's what that capital lambda is. And it returns a regular function. So it's a special function that takes a type. I mean, this is not how it's evaluated at the runtime, but this is how you can think of it at compile time. It's a function that takes a type, and then from that type, which we bind to A, it returns a function on lists of A. So when we apply last to true, false, true, we have capital A dot stuff applied to bool, then true, false, true. And this is actually what's going on at the, I take it back when I said that this is how core, which is an intermediate language, or an intermediate representation that Haskell uses, deals with these polymorphic types. So then you pass in the type bool. So then it says, OK, I want the bool instance of this function last, which I've subscripted last bool. Although I put a list around it, which I probably. And so then it knows which last to apply, which is the last that applies to bools. So, and that's how it resolves that concept of passing in a type is how it resolves type classes. Like every type class creates a dictionary, which is something that exists at compile time that it uses to look up the methods. Okay, so the last rank n types example. I'm just going to answer what this is. It's called a lens. I'll get into why it's useful in a couple of classes. I was going to leave it open, but I think everyone's brain is fried, including mine, so I'll just end on this. And yeah, any questions? And that is not my cat. I picked it because it reminded me of Alanis Morissette singing Ironic.
Oh man, I'm gonna have to. I think you said something along the lines you would advise reviewing the slides. I think that I'm gonna take that to heart.
Sure. I mean, there's a lot of stuff here, and quite honestly, you're already ready to write production Haskell code, like with Google, with a little bit of use of Google to get like some of the systemsy stuff that I haven't covered. You'd be there. You'd be
I
there.
told you.
I got really drunk at his apartment quite a while ago, like 2 Haskell classes in, and I made the boastful claim that I was ready to write production Haskell code.
No, you said you knew Haskell, and then I said, "Can you write production code?"
Oh yeah, whatever. And I wasn't gonna be like, well, no. So I just, I was drunk. I was like,
Can
yeah.
you write non-trivial extensions to GADT?
Yes, I can write non-trivial. No.
Yeah, this is a bit deep today.
Yeah.
Yeah,
I kind of stopped understanding after monad transformers.
Well-
I got that far.
I said monad transformers would be the hardest class. Well, did you understand foldable and traversable?
Yeah,
That
so
does
that
make
makes sense. So it doesn't have a dependency on monad transformers.
So, and then I threw a bunch of
Everything post.
language extensions at you,
Yeah,
probably.
Those were fine.
Okay, well then you understood it.
It's
I
just
mean-
everything that has to do with monad transformers.
They take a while. And to be quite honest, because people find them challenging and because they are not always the right solution, there is PureScript is a Haskell-like language that's being developed to run in the browser, and it uses a different way of stacking it does allow monad transformers, but their effect composition for the browser, because browser effects are usually 2 different things that have nothing to do with each other, like well, let me back up. I shouldn't say don't have anything to do with each other, but usually, let me back up again. Usually you want your monads or your type signature to reflect what the computation can do. And if you think of it in terms of capabilities, it commutes, because if you're saying AT is the ability to do A and BT is the ability to do B, well then folding those into a computation that can do A and B versus one that can do B and A, well, it's the same thing. Whereas, if you look at, say, concrete representations, you commute, or you have like a list of maybes and a maybe of lists. Those are not the same thing. They don't commute. So I think, yeah, monad transformers, you're not the first person to struggle with them. It took me a while. I think if you read the code for the second lab, the list that I provided, that will get you at least some sense of how to use them.
We'll have to go into that lab in more depth at some point.
Yeah, that's.
It's kinda like you kind of like dangled that lab in front of us and then like pulled it away.
No, I did half of it. It just, I didn't realize that Lisp would be as complex as it turned out to be. So.
Languages
What's a quick definition of a monad transformer?
Okay.
Sorry, I'm behind again.
So if you know what a monad is, a monad transformer is a higher kinded type that turns a monad into another monad. And the idea is, so let's take a concrete example. Let's take state port control. So ignore this wrapper stuff. I mean, the meat is here.
Okay.
You have a monad M called your base monad, and you're mapping it into a more powerful monad that has access to some in-program state of type S. So now a stateful action, when you're not thinking monads, we represent a stateful action as S arrow AS. That's a stateful action that returns an A.
And with the state.
Yeah, it updates the state. So for example, increment and return square equals state x to b. And then you could do so then, for example, let my action equal to a return square b. And you run it. You get the updated state. It's been incremented twice, so you get 17. And you get the A, which is 225, and you get the B, which is the 256.
Okay.
So that's state. But we don't just want a state monad. We really want different kinds of state monads for different things that we might be doing. So we say, okay, we have some monad sitting there called M. We define state T as isomorphic to, and this is parameterized as isomorphic to monadic. That's the Clevesley arrow. So that's the function returning in something in the M context. So it's a monadic function in the M monad that takes an S and returns a pair with an A and an S. So that is the monad that has all the capabilities of M, but it has this additional capability, which is the state that lives in this S type. So for example, with this, we have like functions like put and get and modify that are all stateful and allow you to play around with the threaded state that you've got going. You're adding that capability to whatever monad you're wrapping.
So it's an enhanced monad?
Exactly.
So
It's a monad enhancer.
okay, all right,
Yeah.
that makes sense. So
Can it de-enhance? Can you take something away?
That's interesting because almost always a monad expands. There is one case of a monad that doesn't expand, which is called the terminal monad. It's the function. So you can actually do like class foo of A equals degenerate. I'm sorry. That's a monad. That's a monad that takes stuff away, kind of like the constitutive, but you almost never
You're ignoring
see
the
that.
A.
Yeah.
And so there's a lot, the two monads you work with a lot in Rust are the result, and this result is just either, but
Sure.
the implication that the other one is going to be an error.
Right.
Like whatever you gave it. Anyway, either or option, those are the two you use most of the time.
Mhm.
And it's really common to do if you're mapping across stateful, like an array of, or a vector of stateful things, you'll use a map filter or a filter map, which basically on anything that returns a none will be dropped from the array.
Sure.
Or won't be in the new vector that is actually returned. And so it's really common to want to basically there's facilities provided to turn a either into a option, assuming that the left one is success and the right one is failure.
Mm-hmm.
So losing, that's a time where losing the state of that is actually useful. because you're really saying either it works or it's nothing. Like, so.
But this isn't, when I think of monad transformers, or just by the two words, I think of that, but of somehow mapping from one monad to another and completely losing any sort of context that one or the other has. Does that make sense?
It does, but Haskell doesn't want to do that in general because in Haskell you generally use monad transformers to expand capabilities.
Gotcha.
It's up to you as the end user. I mean, yeah, like if you get a maybe event,
It's easy enough to drop context wherever you
yeah,
want.
you can. Oh, you can turn it into an int. What you shouldn't be doing, although with unsafe perform IO you can't, you shouldn't be able to do this. If you're doing this, then you're doing something wrong. But yeah, I mean, monad transformers are a way of, ultimately monad is sort of answering the question, what do we mean by computation? Like, what do we mean by computational effects?
Mm-hmm.
And a monad transformer is a way of taking a monad that has some set of effects and creating a monad that has more capabilities.
So yeah, that makes sense to think about it like an expander rather than a loss of context. Or
Right.
To put it, vice versa, there's also an option. There's also the same sort of mapping from option to result, where you can basically insert. Like there's a type that basically goes the other way, that lets you insert your own error into these options. Like if you're the one doing the computation,
mm-hmm.
right, and you've got some base layer computations that are optional, then you can then wrap all these options up and then insert a custom error type and have it be returned as an either.
Okay.
I've never seen a monad transformer that took away capabilities. And while this guy, the degenerate monad, satisfies the monad laws,
Mm-hmm.
I've never seen anyone actually use it, ever. Monads, because the monad has a function return, of course, which takes A's into that monad, and it's almost always injective. Like it's almost always an expansion. So there are, like with lists, you have all of the single elements lists containing the A's, but you also have multiple element lists in the empty list. So you're expanding the universe. And every monad I've seen expands. It doesn't, it expands. It doesn't take away.
That makes sense.
You can take away at the end. For example, when I had this guy, my action, it's like, okay, so this is living in some state monad, but really I don't want a state monad action. I want to actually run the state on the number 15, and there we go. We've turned it into a pile of numbers.
Is there a concept for, and this might be close to what you're talking about, Zach, like inverting two monads? So like you have a list of maybes and you want to translate that into a maybe of a list?
You're talking about commuting. So
Isn't that actually joining, not commuting?
no, join requires that they be the same monad. The reason for the monad transformers is because, and as I talked about before, like with applicatives, they will compose an applicative. So if F is an applicative and G is an applicative, then this is obviously pseudocode because I'm using a lambda expression and the A is actually a type. But this form as a function of A will also have a natural applicative. But with monads, that's not the case. And the reason is because there's no way to go from they're fundamentally different things. They have fundamentally different capabilities.
Right. Okay.
Traverse, though, is kind of a commutation. Or not traverse, actually, but if you look at sequence A, which is traverse id, that is a commutation. And yeah, there's actually been a lot of work that people have put into studying, isomorphisms of types. For example, in a meaningful way, these types are all the same because they contain all the same things, and there's like a natural transformation between them. So people have studied that. People much more into the abstractions than me. I mean, my goal is just to build some production Haskell software over the next 12 plus months.
Yeah.
Not necessarily to solve all of mathematics.
Right.
I've heard that that's hard to do.
Yeah, and I heard like you can't really do it anyway, right? So.
Well,
Completeness.
I mean, it depends on how we model. Depends on how we model consciousness, actually.
Oh God, we already went. Yeah, everything always goes down to that, doesn't it?
Because yes, I mean, but certainly, even if you had infinite consciousness capability, you would be communicating through a finite alphabet, you'd be communicating through an alphabet with a finite number of symbols, which means that all those Gödel and Turing and Rice results just bite you in the ass. So yeah.
So we're always screwed.
If you're not screwed, you can't prove to anyone else that you're not screwed. So.
This got deep real quick. Okay, but yeah, that makes sense. Because I find myself trying to think about that when I'm dealing with contexts and like flipping contexts, like the example, and I was like, this is impossible. I can't, because you would have to define your own semantics, right? Before that, and they may or may not make any sense.
Mm-hmm.
Here. So this is actually, I'm doing exactly what you said. You said turning the result. So basically, I was writing tab completion for my shell that I've been working on. And one of the things that it would do is that it would basically, if it didn't have permission to see a file, like if it was iterating, basically there were errors on some files. It was like, I can't do anything with that file. It's going to return like an error or a none. I think it was a result at the time.
For each file, for each item.
Yeah, for each item. And so I have a big list of things that I might view as candidates for tab completion, but I have to basically turn a list of, results into a result of lists at some point, which I might have, or a result of a list, basically because I considered just saying error if I can't read some of the things, and I didn't. But you actually literally, the way, all you have to do is say, you just have to call .collect on that. I just realized I took that part out. You have to call, by giving it.
Before we diverge, do we have any more Haskell questions, or shall I?
Sorry.
Shall I turn the broadcast off?
You're still broadcasting.
Yeah, I always broadcast until the end. But do we have any more Haskell questions?
Kind of like the extra code section.
If you have a type constructor that's more than one parameter, do you have to partially apply it to get it to be monadic?
Well, yeah, because so for example, either has kind type arrow type arrow type, and so either is not a monad. That doesn't make any sense.
Well, if you partially apply the first.
Exactly. In fact, I can write the instance right here. Return x equals write x, and left some error, find anything. Could be left of that error, and otherwise, if we have write b, find some f, then we get fb. So that's either is a monad. Oh, except that up there is wrong. What I mean is instance monad either e.
And if you're pattern matching, does it give you a warning or compilation error if you don't cover all cases?
Pattern matching, non-exhaustive. Yes, you can turn compiler errors on. I think -w all will give you a warning of a non-exhaustive pattern match. So
That's great.
yeah,
I don't know if F# does that, but it always annoyed me that I didn't have that.
I think it does.
And F# it's a warning.
Yeah, isn't the warning?
Yeah, you get a
Probably
warning.
turn-
I want it to break. Like,
you
I
can
wanna
make
know
warnings
that.
errors. but
Yeah, I think you can make it an error. I'm not sure.
Okay.
It definitely warns you though. Like it'll underline.
Yeah, I usually unclick that in Visual Studio. I don't want to see the warning show there with the errors. So I have one more general question, more
Sure.
not about Haskell, but so I was reading a little bit about the type system, and they were saying that you can think of types as sets. So like an int is a set of things that start at negative int, right, or negative 2 billion, whatever,
Okay.
all the way to positive, right? And I always, when I've been doing my reading about functional languages and Haskell, I've been trying to understand why people say category theory is like involved in this whole thing. And is that why? Is because like the generalization of a set is a category, and then you've kind of taken like that logical leap?
Okay, so I'm way out of my depth on category theory. Like I said, I'm more of a pragmatist. I'm into Haskell for its practical value, not for its category theory. So, but my understanding is that sets are a category. I think the objects are the sets and the morphisms are the functions from sets to sets.
Okay.
A type is not quite the same thing as a set.
Okay.
And the reason I say that is because, for example, you can create, I did it wrong there. Yeah, okay, so you can create like a new type that, you know, is exactly the same set. The only difference between the new type and the old type is that the type checker knows that the new type follows different rules. You know, so for example, if you have a function, and you pass it 17, it fails, but if you pass it the n, then it, well, that would be fine, except for the fact that it doesn't have a show. So if you, there you go. So type is a little bit different from set. It's kind of like a labeled set. The other thing is that sets can intersect, whereas types don't intersect.
Oh.
So like the 5 that lives in int is a totally different thing from the 5 that lives in word 64, the 5 that lives in double.
Yeah.
Cross-type equality is something that generally people argue does not make sense. Equality is bound to a specific type.
I see.
So a type is a set, or it has a set of values, but it has other stuff in it. And yeah, you're not wrong to say a type is a set. It's just that there's other stuff attached to it.
Yeah, I was trying to figure out where it breaks, because it's just an analogy, right? I was trying to figure out where it breaks, and that is a good example of where it breaks.
There's a blog series called Category Theory for Programmers. It's pretty good.
Really?
Just Google that and probably find it. I like to read it, but I don't understand any of it.
All right, I'm going to drop
I
off
love
the
it.
broadcast.
I do that every day.
We are going off the air.
Cool. Oh, is my